So this is questions on magnetism. Shown below here is a diagram of a bar magnet with the north and the south pole indicated, showing you the shape of the magnetic field both inside and outside of the bar magnet. The symbol B, of course, is the magnetic field strength. Alright, first question talks about an electric motor consisting of a rectangular coil with 150 turns, 0.2 meters long and 0.12 meters wide. The coil has a current of 0.26 amps through it and is parallel to a field of magnetic flux density 0.36 Tesla. Find the torque exerted on the coil. Now I'll just draw a diagram of the coil and how it's situated. So there's the diagram. Just to explain what's happening here, we have a coil, the black rectangle. The current I is shown, so the current's moving this way. And I've labelled the points A, B, C and D of the corners of the coil. And we are going to consider the direction that it spins later on, have this position down here as our point of view. So if we're imagining looking at the coil from this direction, here's the length 0.2 meters and the width 0.12 meters. Notice the magnetic field, B field, the magnetic field is running along these blue lines here. So you can see that lengths AD and BC are parallel to that magnetic field, and it's only lengths AB and DC which are at 90 degrees or perpendicular to that magnetic field, which is important, of course. So the reason it's important is because it tells us straight away that the force acting on lengths AD and BC must be 0 newtons, since they are not at all, there's no angle between them. If you look at the general equation for the force due to the magnetic field and a current along a certain length times sine of the angle, since if the angle is 0 degrees, of course, the force is 0 degrees. But if we consider the force acting on a single wire along length AB to start with, we will have BIL times sine 90. Now sine 90, of course, is 1, so that's the maximum value that the force can take. So if we substitute in the magnetic field strength 0.36 Tesla and the current 0.26 amps and that length 0.20 meters, we end up with the force along a single wire AB as 0.1872 newtons. Now, since the same force acts on length dB, we actually produce a couple, and so we can calculate the torque as force times distance. So just substituting that force in and multiplying it by the width of the coil, 0.12 meters. So you'll be multiplying 0.1872 times 0.12. You get the torque produced due to one single wire as 0.0022464 Newton meters. Now we need to multiply that by 150 to get the final answer. So doing that, why? Because we have 150 turns, so that this same torque will be simply multiplied by 150. So we get our final answer as 0.34 Newton meters to two significant figures. Now, thinking about the direction, from that point of view that I showed you just before, you need to use your right hand slap rule or perhaps Fleming's left hand rule, and if you do it correctly, you should come to the conclusion that the coil will move clockwise, or this torque, this couple acts in a clockwise direction from the point of view indicators. Question 2, calculate the magnetic flux density, that's capital B of course, 20 centimetres from a conductor carrying 4.5 amps. So we're going to use this equation involving the permeability mu naught of free space times the current over 2 pi and the radial distance from the wire. So if we sub the numbers in for that first part, part A, you should be calculating 4.5 microtesla, which is 4.5 times 10 to the power of negative 6. And B, 2 wires each carry 4.5 amps in opposite directions and are separated by 10 centimetres. Find the magnetic flux density at point P on the diagram below. So to find the magnetic flux density there, we need to consider the magnetic field flux density caused by this current in this wire, using this equation again, and also calculate the magnetic flux density caused by this current in this wire. Now from here to there, to that point P, is actually 0.32 meters. We must use meters. So if you use that in this position here for the radial distance, the current is the same in both wires, 4.5. You should calculate for that wire, the furthest wire, a figure of 2.8, take all the figures at this stage, 1.125 microtesla. Okay, that's for this wire here. Doing the same calculation using the same formula for this closer wire at 0.22 meters for the radial distance, you would calculate 4.0909 microteslas, taking all the figures at this stage. Now, the question is what do we do with these figures? Do we add them or subtract them? And the answer is we subtract them, because the two currents are in opposite directions, so the magnetic flux density, the field lines, if you like, at point P will be acting in opposite directions, and therefore there'll be some cancellation occurring, and so subtracting those figures is the thing to do. So finally we can calculate the field at P to be 1.28 microteslas. Question 3. When a particle with charge q moving at a given velocity v enters a uniform magnetic field, it will move in a circular path of radius r. Derive an expression for r in terms of this velocity, the size of the charge and the strength of the magnetic field. So the first thing to remember is that we're going to get a centripetal force produced, and it's going to be directly equal to the size of the magnetic force on that charge. So that's BQV equals mv squared over r. So rearranging, we can just cancel out the v and the squared, and making r the subject of this equation, bring it across, so we have mv over bq as our final expression. So this question continued. A uniform magnetic field of strength 4 millitesla is used to deflect a beam of electrons into a circular path of diameter 65 millimeters. Calculate the speed of the electrons. So we're going to use that expression we just derived, but rearrange it to make v the velocity of the subject. So that's going to be bqr over m. For electrons, we need to know their charge, 1.6 times 10 to the negative 19 coulombs, and the mass of a single electron, a very tiny 9.1 times 10 to the negative 31 kilograms. So if we sub that into this equation, and we use 4 by 10 to the negative 3 for the magnetic field strength, capital B, and 0.065 for the, no, we divide that by 2 in fact, because that's the diameter. There's a bit of a trick. So So that's diameter. Of course, this is the radius. So we need to divide that by 2. Okay, so if you manage to plug that in, you should be getting an answer, quite a large velocity. 2.3 times 10 to the 7 meters per second. The two significant figures. Question 4. A proton of mass m and charge plus q is travelling through a vacuum in a straight line with speed v. It enters the region of uniform magnetic field of magnetic flux density capital B, as shown. The magnetic field is normal to the direction of motion of the proton. Explain why the path of the proton in the magnetic field is an arc of a circle. So to explain this, you need to talk about two things with 2 marks. So since the velocity is normal to the magnetic field, the force due to BQV, the magnetic force, BQV, acting on those charges, acting on the proton in this case, will also act perpendicular to the direction of motion. Now, this will cause a centripetal force effect on the proton, which makes it move in a circular arc. That would be with 2 marks. So, question 4 continued. The angular speed of the proton in the magnetic field is omega. Derive an expression for omega in terms of B, Q, and M. So once again, we start with the force of the magnetic field must be equal to the centripetal force effect in this case. So we have B QV equals, now we want to use, of course, the form of the centripetal force involving omega. So that's omega squared. So now we simplify. In fact, we need to replace this velocity also with omega. So we can do that. Just recalling, of course, that velocity equals r omega. Put that in. So BQ r omega equals m r omega squared. And now we can cancel some things out here. We can cancel the r's out. We can cancel that omega and the squared away. And it becomes quite obvious that the expression we need is omega equals BQ divided by m. So there we go. Done. It's fairly generous, 4 marks. This is from a past paper. But yes, if you remember this derivation, it's not that bad.